Good evening, chemistry students. Yes, you may notice my paper is a little written on, but I had to go back and start over because I had to rethink about some stuff, and I want to make sure I tell you the right stuff. So, today we're talking about thermochemistry, and thermo simply means heat. In chemistry, we don't have hot or cold, we have hot, warm, and not so warm. Okay, we don't identify cold, but if you say that, it's okay. So, we'll start off by matching terms. So, I just did a couple of them. Did a simple one like F takes up space and has a mass. Well, we know that's matter. And then another one that's a vocabulary word throughout this unit because there's a lot of vocabulary is G, measure of randomness and disorder. Well, that's entropy. Okay, and I'll do another one. Heat can be transferred through electromagnetic waves. And that's the way the sun rays travel, and that is called radiation energy. Okay, so those are the three matching. If you go down here to the middle part, you're looking at, is this an energy or is this a matter? And so I went through and did a couple of these. The thing that you have to remember is if it's in a wave, okay, so in a wave such as sound, light, radio, those are all energies. Okay, electricity is also in a wave. You can't see it, but if you look at computer screens or you look up at fluorescent light bulbs, they're in waves. It's hard to see. You have to have special stuff. They say some people can see them, and sometimes those people see them and then start having seizures. Hot heat is also a heat wave. You're like heat wave, yeah. Okay, so that's an energy form. Then you have things like water and air. Those are forms of matter. Milk. Who would have thought milk was matter? All right. And so then we get into endo and exothermic reactions. And so with endo and exothermic, so exothermic releases energy, it feels warm. Okay? But it has what we call a negative delta H, which is enthalpy. Okay, and enthalpy is the amount of heat within a system. Endothermic absorbs energy, feels cool, and this is going to have a positive delta H. And so as we go through these, we're going to, first off, we'll just do some of the naming. Well, a solid to a liquid. And so if I think of water as my example, well, a solid would be ice. And then I'd have liquid water. And to get ice to go to liquid to water, it would just melt it. So this is melting. And then let's do another one, liquid to gas. So if I take my water and I convert it to steam or whatever, then this would be boiling slash evaporation. Okay, so like in the clouds, the water doesn't boil and go into a gas, it evaporates. And let's do one last one, a gas to a solid. So gas, let's say I start off with carbon dioxide, okay, and end up with dry ice. There's no liquid phase, it's just solely a gas to a solid. And so this is called deposition. Okay. On day 2 of your notes, we'll be covering this material. What are these actually called? You have these in a prior unit. I think it's unit 2, unit 1, 2, or 3. I think it's unit 2. And on the front page of the notes, there was a triangle that showed these and what the different states were and what we call these. So please refer back to your notes if you want to work on this. Now, what you have to think about is what's happening with the energy in these different state changes. So, for example, to go from a solid to a liquid, I'm going to need to put energy in it. So, energies have to go into it. So if I'm putting energy into it, then these are endothermic reactions. So anytime you look at these, you always think about, so from a liquid to a gas, am I putting energy in or am I taking energy out? Well, I'm putting energy in. I'm increasing the entropy, which is the randomness of the molecules. As a liquid, they're just kind of very close to each other, kind of moving around. As a gas, they're all over the place. And so this is also an endothermic reaction. Now, if we look at gas to solid, well, you have the gas molecules all over the place to get down to solid, and they're just right next to each other, just quivering in their location. But they're very uniform. So to go from a gas to solid, I have to get rid of energy. I have to pull it out. And so when I get rid of it, that becomes an exothermic. Okay, so try these other three on your own. Let's go to page 2. And so when we get to page 2, now we're looking at other 3 things. We have conduction, convection, and radiation. So conduct, the way I think of it is the D is direct. Okay, I take my hand and I put it on a hot stove. It hurts. That's conduction because the heat is touching me directly. Okay, convection is through air currents. So this is the way the weather works. This is the way ovens work. If you ever get a chance to go into a commercial kitchen, they have a bunch of convection ovens that cook food. And then when you think of radiation, think of the sun. So things that are radiate. The sun radiates. So if you draw Mr. Sun, Mr. Golden Sun, his sun rays are radiating to you. Okay, so let's go through a couple of these and see how we do. So hot coffee is stirred with a spoon. The spoon gets hot due to, and you probably said, conduction. And that would be correct because the hot coffee is directly touching the spoon, so it's conduction. If you scroll down to C, near the ceiling of a room, the air is warmer. Okay, you've always heard warm air rises, and that is because of convection. Okay, and like I said, this is, if you remember learning about weather, I think it was about 6th grade you learned about some weather. You may have heard it again in 8th grade. Okay, let's continue on. So if you look at F, in a swimming pool, the water near the surface is slightly warmer. The warm water rises because, well, that's once again, that's the convection. Okay. Now, if you go down here, all right, so if we look at J, huge rock at a state park gets so hot during the day that you can't sit on it from. Well, what would make that rock hot? Well, it's not a heat lamp, but it would be radiating energy from the sun. So that would be radiation. Okay? And actually, if you ever get to go out to Enchanted Rock and you stay the night at Enchanted Rock, this is very true. I used to go out to that area and we would go lay on a huge piece of granite rock at night, and it would be 12 o'clock at night and 50 degrees outside, but that rock was nice and warm and cozy. Just curl up on it and go to sleep. It was just so comfortable. And actually the bats would fly over our heads. You had to be careful of the bats try and attack you sometimes. Okay. You go down here. So when you walk on the beach in July, the sand feels hot because, well, is heat being transferred? If it feels hot, heat has to be transferred. So it can't be A because it says no. That's wrong. Heat is absorbed into your feet from the sand, so it feels hot. Okay. Heat is absorbed by the sand from your body, leaving you feeling hot. or heat transfers from the ocean to the sand. Well, we didn't talk anything about the ocean, so it can't be that one. So now we look at, so how is the heat transferring? Heat is absorbed into your feet from the sand, so it feels hot. Or heat is absorbed by the sand from your body. Ooh. Well, all right. And so it would be B. The heat is absorbed into your feet from the sand, so it feels hot. Okay. All right, go down here. When a material condenses or freezes. Okay, so we're going to freeze it. So freezing would be a solid. And to go to a solid, you would have to go from a liquid. And so when you go to a solid from a liquid, what's going to happen? Well, can it not be measured? Well, that's not true. Will not change? Well, we know that's not right. So it's either going to be absorbed or released. So what is the energy going to do? Well, the energy has to be released so that the molecules can slow down. So slow down molecules. Energy is released. So your answer is C. Okay, so whenever you get questions like this, always think about, okay, so what does that mean? What is it doing? Which way is the energy flowing? What is going to happen to the entropy and the entropy? All right, so last page for last thing of homework for day one, and we'll start with looking at number 2. So first off, you have to figure out, is this graph endothermic or exothermic? Okay, and the way it works is you look at the graph, and if it starts really low and goes up and then back, and so basically this starts low and this ends higher, this is an endothermic reaction. Okay, so now delta H. Well, if you know it's endothermic, you know delta H has to be a positive. And so now we're going to figure that out. And so you always go final minus initial. So it's about 30 kilojoules minus, and we'll say that's about 10. So it would be a plus 20 kilojoules. Okay? So all we did was final minus initial, or ending minus beginning. Okay? Lastly, same with activation energy. So it's going to be the very tip top, because remember, this is our activation energy. This is called E sub A. And so you take, this is 45 minus 30. Okay, you get positive 15 kilojoule. Okay, so all I did was subtract. So this is 45. This is 30, because right where you want to, right where this ends, you want to be able to subtract those two numbers, the top of the hump from the bottom of the hump. And so it's 45 minus 30, and it gives you a plus 15. Okay. So let's look at number 6 down here. So this one, we're starting high, ending low. So whenever we start high, end low, this is an exothermic reaction. Well, we know exothermic, the delta H is always negative. So we're going to subtract final minus initial. So we start with final. So that's a negative 40. So remember, final minus initial. So negative 40 minus. And so this looks to be like a negative 20. Okay. So whenever you have this, remember these because you have a subtraction and it both becomes positive. So negative 40 plus 20 is a negative 20, and that's kilojoules. Okay, activation energy, figure the same way. So figure out where it starts at, and then figure out the top of the hump. So it looks like about 10, this line right here, so it'll be 10 minus, and then it's down here negative 20. And so remember that subtraction of negative makes positive. So remember, these are your reactants, and these are your products in a exothermic reaction. And so for the reactants to start producing the products, it takes, in this situation, 30 kilojoules to get to go. Okay? Over here, these are reversed. I didn't talk about these, but in an endothermic reaction, your reactants are down here. Your reactants are down here, and your products. Okay, so it's what we call it's actually a mirror image. It's a flip image. So reactants start high, end low, and endos, so start high, end low. Endothermic, because we're going to absorb energy, we're going to start low and end high. All right, so that's all the homework help for day one. So good luck and have fun.